Hello everyone. In this video, we'll be doing a numerical problem based on boundary value problems for solving Laplace equations. In this question, it is asked to find the field of coaxial conducting cylinders, and you have two boundary conditions. One is V equal to 50 volt at rho equal to 2 meter and V equal to 20 volt at rho equal to 3 meter. We are asked to find the electric field at the given point P with the coordinates 3, 1, 2. And for the second subdivision, it is two radial conducting planes are given and the corresponding boundary conditions are also given. For the first subdivision, we should consider voltage as a function of variable rho because the boundary conditions are given for the variable rho. So let us do the first subdivision. And for the second subdivision, the voltage between these two boundary conditions is a function of phi. We will do it accordingly. First, let us start with the subdivision 1 and complete it, then go for the next subdivision. For the subdivision 1, you have two coaxial conducting cylinders given. So let me roughly draw two coaxial conducting cylinders. The inner one is at a radius 2 meter and the outer one is at radius 3 meter. Now the inner one is at a potential of 20 volts. Inner one is at a potential of 50 volts and the outer one is at a potential of 20 volts. Now the two boundary conditions are given. I will be writing the boundary conditions. At radius 2, potential V is 50 volts and the second boundary condition is at radius 3, potential V is 20 volts. Now let us consider the potential function as a variable of rho. Now we will be writing the Laplace equation in cylindrical system. This talks about cylindrical system. Now when we write the del square V for cylindrical system where V is only a function of rho, differentiation with respect to only rho will be non-zero. Differentiation with respect to phi and z will be 0. So I'm excluding those two terms, writing only the term for differentiation with respect to rho. So this is del square V and the second term with respect to phi will be 1 by rho square, dou square V by dou phi square, and the last term is dou square V by dou z square equals to 0. This is del square V in cylindrical system, and we know V is only a function of rho, thereby potential function differentiation with respect to phi will be 0 and z will be 0 because V is only a function of rho. Thereby we have only this first term, 1 by rho d by d rho of rho dv by d rho equals to 0. This only is left. Now we can consider this d by d rho of rho dv by d rho equals to 0 because when I bring this 1 by rho to the right hand side, that will be multiplied with 0 and you'll get 0. Now integrating once with respect to rho. So integrating once with respect to rho will give rho dv by d rho equals to integration plus constant. Next, you will be getting dv by d rho equals to c1 by rho. Integrating one more time with respect to rho will give v equals to c1 logarithm rho plus c2. Now we have to apply the given boundary conditions for this function. So the given boundary conditions are at rho equals to 2, V is 50 volt and at rho equals to 3, V is 20 volt. By applying these boundary conditions, we will be getting the constants C1 and C2. So let us apply the boundary condition. First boundary condition, if you apply 50 equals to C1 logarithm 2 plus C2. Applying the second boundary condition, you'll get 20 equals C1 logarithm 3 plus C2. Now solving for these two equations, you'll get constant C1 and C2. I'm leaving the solution as your exercise. You know how to solve two equations with two unknowns, and As a result, you'll be getting the C1 value as minus 73.989 and C2 value as 101.285. So substituting this C1 and C2, you'll get the potential V, which is a function of rho, that is minus 73.989 logarithm rho plus 101.285. So this is the potential V between the two cylinders. Now we should find what is electric field intensity vector E. So E vector has to be found as minus del V. We can write the formula for minus del V, minus dou V by dou rho A rho cap plus 1 by rho dou V by dou phi A phi cap plus dou V by dou Z A Z cap. Here in this, we have voltage function of only rho variable. There are no phi and z variables, so their corresponding differentiations will be 0. And you'll be getting E vector as minus differentiation of this with respect to rho will give minus 73.989. Differentiation of logarithm rho is 1 by rho A rho cap. And this is the electric field intensity. The unit for electric field intensity is volt per meter and the unit for voltage function is volts. Now, in question, you are asked to find the value at the point P. At point P with coordinates 3, 1, 2. So we have to find the value of electric field intensity at this point P. Now, we should find what is the value of rho at this point P. This point P has the coordinates x, y, z. I need to find what is the value of rho. The formula to find rho from x, y, z values is x square plus y square. Under root x square plus y square gives rho value. So from this, we can find electric field intensity. So minus 73.989 divided by root of, here x is 3, root of 3 square plus 1 square, or you can write which is under root 10. This is rho. So under root 10 A rho cap volt per meter. Or we can write the magnitude of E as asked in the question, which is 73.989 divided by root 10. You can calculate it and this value will be 23.397 volt per meter. This is what asked in the question for the first subdivision. So this is the electric field intensity at the point 312 between the two coaxial conducting cylinders. Now let us proceed to do the next subdivision. The second subdivision talks about two radial conducting planes. So let me consider two radial conducting planes with two angles of phi. So first one is at phi 10 degrees and second one is at phi 30 degrees. Now between these two, potential will be a function of phi and we have to consider the boundary conditions. Let me write the boundary conditions. V equal to 50 volt at angle phi, which is 10 degree, but we should write this in radians in order to substitute in the equation. And V equal to 20 volt at phi equals to 30 degrees. We should write this also in radians because in the equation, we will be writing the angle phi in radians. You can calculate using the calculator where this 10 degrees will be equivalent to pi by 18 radians and this 30 degrees is equivalent to pi by 6 radians. Now we can consider these boundary conditions and solve for the Laplace equation to get the potential function, which is a function of phi. So we know Laplace equation is del square V equals to 0. In cylindrical system, it is 1 by rho, dou by dou rho of rho, dou V by dou rho, plus 1 by rho square, dou square V by dou phi square, plus dou square V by dou Z square equals to 0. Now here we know V is only a function of phi. Thereby, differentiation with respect to rho and z will be 0. Only the differentiation terms for phi is non-zero. This makes the expression 1 by rho square d square v by d phi square equals to 0. Now this 1 by rho square, if I bring it to the right hand side, multiplying with 0 will give 0. The differential equation is d square v by d phi square equals to 0. Now we have to integrate with respect to phi twice to get what is the function v. Integrating with respect to phi once will give dv by d phi, and integration of 0 is 0 plus integration constant c1. Now one more time integration with respect to phi will give potential function, which is v equals to c1 into phi plus integration constant c2. Now this is v. By applying the boundary conditions, we have to find the constants c1 and c2. So let us take these two boundary conditions, and we have to apply the boundary conditions for angle phi in radians. So we should be applying these boundary conditions to get the constants c1 and c2. First, applying this boundary condition, we'll get 50 equals c1 into phi is pi by 18 plus c2. It must be used in radians. So the angle phi must be used in radians. For the second boundary condition, 20 equals c1 into pi by 6 plus c2. Now by solving these two equations, we will be getting the constants c1 and c2. So I'm leaving that solution for your exercise. I'll give the constant c1 and c2. You can pause the video and find the answer and verify it. C1 is minus 85.9436 and C2 is 65. Applying these two, you will be getting the potential function V, which is a function of phi, as minus 85.94365 plus 65. So this is V, and the unit of V is volts. Next, we should find what is electric field intensity. We should find electric field intensity, which is negative gradient of potential, which is minus dou V by dou rho A rho cap plus 1 by rho dou V by dou phi A phi cap plus dou V by dou Z A Z cap. Now, taking this potential function V, differentiating with respect to phi. So this has only phi term. There is no rho variable or z variable. Their corresponding differentiations will be 0. Now taking this, differentiating with respect to phi and multiplying with the constant which is already available, minus 1 by rho into differentiation of this with respect to phi is minus 85.9436 plus 0. A phi cap. Sorry, it must be A phi cap. Now this will be 85.9436 by rho A phi cap volt per meter. This is the expression for electric field intensity between the two radial conducting plates. Now we should find the value of electric field intensity at the given point. We can find the electric field intensity at point P, which has the coordinate 3, 1 and 2. For this, again, we should find what is the value of rho and substitute. We know rho is under root x square plus y square. Here x is 3 and y is 1, which gives root 10. Thereby, we will get electric field intensity as 85.9436 divided by root 10 A phi cap volt per meter. This is the electric field intensity, and we can write the magnitude of electric field intensity by solving this with only the magnitude, which turns out to be 27.177 volt per meter. So this is the electric field intensity at point 3, 1, 2 for the second subdivision between the two radial planes. I hope you have understood this problem. Thanks for watching the video.